Every single night you look up and there it is, the moon. Bright, familiar, constant. Except it's not constant at all, it's leaving. Right now, this very second, the moon is drifting away from Earth at 3.8 centimeters per year. The speed your fingernails grow. You won't notice it tonight or next week or even in your lifetime, but over 4.5 billion years, that drift tells a story stranger than most people imagine. The reason behind it involves ancient collisions, oceanic friction, stolen energy, and a cosmic dance that's been playing out since before anything lived on this planet. Most people think the moon just orbits us like some predictable clock. They don't know about the angular momentum transfer happening in shallow seas right now. They don't know about the 5-hour day Earth used to have. They don't know that fossil corals from 400 million years ago prove the drift has been consistent and measurable. They definitely don't know about the tidal dissipation occurring in the European shelf, the Patagonian shelf, and the Bering Sea at 3.64 terawatts. The moon isn't just floating away, it's being pushed by the very oceans it controls. If you value documented astronomical and geological history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. The script is researched and factual, using sources from the lunar-laser ranging data published in Science Journal by Williams and colleagues in 1994. Showing millimeter precision measurements from retroreflectors placed by Apollo astronauts, and from the Nature Geoscience paper by Mitchell and Kirscher from June 2023, analyzing tidal rhythmites that constrain Earth's rotation history across billions of years. Now back to the information. Let's start with how we know the moon is moving. July 21st, 1969. Apollo 11 lands on the moon at Tranquility Base. Buzz Aldrin and Neil Armstrong deploy a suitcase-sized panel with 100 solid fused silica corner reflectors. Each cube 3.8 centimeters in diameter. These aren't cameras or sensors, they're mirrors, precise geometric mirrors designed to do one thing: reflect laser beams fired from Earth back to the exact source. August 1st, 1969. Lick Observatory in California fires a laser at the moon. They detect the return signal, 7 meters of accuracy on the first attempt. By the time Apollo 14 and 15 placed their own arrays in February and July 1971, the system works at 15 centimeter precision. Today, the Apache Point Observatory lunar laser ranging operation in New Mexico achieves 1 millimeter precision. 1 millimeter across 384,400 kilometers. That's measuring the distance between Los Angeles and New York to within the width of a human hair. The measurement is simple in concept. Fire a laser pulse, wait for it to bounce off the retroreflector, measure the round trip time. Light travels at 299,792,458 meters per second. The math is direct. Every measurement over the past 54 years shows the same thing. The moon recedes at 3.8 centimeters per year. Not 3.7, not 3.9, 3.8. The retroreflectors don't lie. The Luna 21 mission placed a French-built retroreflector array in January 1973. The Soviet Lunokhod-1 rover carried 14 triangular cube reflectors, each side 11 centimeters. Lunokhod-1 went silent for decades. March 2010, NASA's Lunar Reconnaissance Orbiter locates it again. The array still works. 5 retroreflectors total sit on the moon right now. Apollo 11 at Tranquility Base, Apollo 14 at Fra Mauro. Apollo 15 at Hadley-Rilla, with a panel 3 times larger than the others. Lunokhod-1 in Mare Imbrium. Lunokhod, 2 near Le Monnier Crater. India's Chandrayaan. 3 added a 6th in August 2023. All 5 original arrays confirm the drift rate. 3.8 centimeters per year. Some scientists call this rate anomalously high, but it's not an anomaly. It's physics playing out in real time. Why does the moon drift? The simple answer is tides, but tides don't work the way most people think. The moon's gravity pulls on Earth. The water closest to the moon accelerates toward it faster than Earth's solid mass. The water on the opposite side accelerates slower. This creates 2 bulges, one facing the moon, one facing away. If Earth didn't rotate, those bulges would align perfectly with the moon. But Earth spins once every 24 hours. The moon orbits once every 27.3 days. Earth's rotation drags the tidal bulges forward. The bulge facing the moon leads it by about 3 degrees. This misalignment is everything. The near side bulge pulls the moon forward in its orbit. The far side bulge pulls it backward, but it's farther away, so the force is weaker. The net effect is a forward tug. That tug accelerates the moon. When the moon accelerates, orbital mechanics does something counterintuitive. The moon moves to a higher orbit and slows down. The faster the moon goes, the more hours, the farther out it spirals, The farther out it spirals, the slower its orbital velocity becomes. Right now, the moon orbits at 1.02 kilometers per second. In the distant past, when it was closer, it moved faster. Conservation of angular momentum demands this, but there's a cost. Earth pays the price. The tidal bulges don't move for free. Friction between ocean water and the seafloor resists the bulge's motion. This friction converts Earth's rotational energy into heat. 3.78 terawatts of power extracted from Earth's spin every single day. 3.64 of those terawatts dissipate as heat, most of it in shallow seas. The European shelf around the British Isles, the Patagonian shelf off Argentina, the Bering Sea between Alaska and Russia. These regions account for 70 to 75% of global tidal dissipation. The remaining 25 to 30% dissipates in the deep ocean near rugged topography. Seamounts, mid-ocean ridges, places where tidal currents generate internal waves that break and create turbulence. The energy loss slows Earth's rotation, 0.0016 seconds added to each day every century. Doesn't sound like much. Over 4 billion years, it adds up to everything. The length of a day has stretched from 5 hours at the moon's formation to 24 hours now. The moon has moved from roughly 2.9 Earth radii to 60.3 Earth radii. The angular momentum lost by Earth's spin transfers to the moon's orbit. Total angular momentum in the Earth-Moon system stays conserved. Energy dissipates. Angular momentum doesn't. This is the cosmic accounting that governs planetary motion. The tidal bulge isn't a simple bump in the ocean. It's a complex wave pattern that depends on ocean basin geometry, continental positions, water depth, and resonance effects. Shallow seas amplify tidal currents. The Patagonian shelf experiences some of the strongest tidal regimes on the planet. About 10% of global tidal energy dissipates there. Tidal fronts form where strong currents around headlands like Peninsula Valdez generate vertical mixing. The water stratifies in summer when solar heating warms the surface. Tidal mixing breaks that stratification. Fronts appear at the boundary between mixed and stratified water. These fronts are zones of high biological productivity. They're also zones of maximum energy dissipation. The M2 tidal component, the principal lunar semi-diurnal tide, accounts for 2.5 terawatts of the dissipation. The rest comes from other components: S2, K1, O1. Solar and lunar effects combined. The M2 tide dominates because it has the strongest forcing and the highest amplitude. In some regions, M2 tidal amplitude reaches over a meter. The currents can exceed 2 meters per second. That much water moving that fast over rough seafloor generates enormous friction. The European shelf around Britain shows similar patterns. The English Channel, the North Sea, the Irish Sea. These are all hotspots for tidal dissipation. The Bristol Channel in particular experiences tidal ranges exceeding 14 meters during spring tides. Spring tides occur when the sun and moon align. Their gravitational effects add together. Neap tides occur when the sun and moon are at right angles. Their effects partially cancel. The difference between spring and neap tides changes the tidal range by a factor of 2 or more. This variation affects energy dissipation. Spring tides with faster currents deposit thin sediment layers. Neap tides with slower currents deposit thicker layers. These layered deposits are called tidal rhythmites. They preserve a record of ancient tidal patterns. They're one-way scientists reconstruct Earth's rotation history. We can test the moon's drift using evidence from the deep past, fossil corals, tidal rhythmites, stromatolites, growth rings, and ancient mollusks. All of these natural archives record how fast Earth was spinning millions of years ago. Cornell paleontologist John Wells made the breakthrough in 1963. He examined Devonian corals from central New York. Corals grow daily bands in their calcium carbonate skeletons. Modern corals average 360 lines per year. Wells counted the bands in Devonian corals: Heliophyllum, Iridophyllum, Favicites. He found roughly 400 lines per annual growth cycle, 400 days per year. The year hasn't changed length. Earth's orbit around the sun remains constant at 365.25 days. But if a year contained 400 shorter days, each day was only about 21.9 hours long. The Devonian period dates to roughly 380 million years ago, based on radiometric methods. If Earth's rotation has been slowing at the current rate of 0.0016 seconds per century, we can calculate backwards. 380 million years times 0.002 seconds per million years equals 7,600 seconds. That's 2.11 hours. A day would have been 21.89 hours long. Wells found 400 days per year. The prediction says 396 days per year. The match is almost exact. Wells then checked Carboniferous corals from about 350 million years ago. He found 390 lines per annulation. The prediction for that time is 385 days per year. Again, close agreement. The coral data isn't perfect. Some corals show variation. Some scientists argue that daily growth isn't always reliable. Environmental factors can disrupt banding. But the overall trend is consistent. Older corals show more days per year. Younger corals show fewer. The pattern fits tidal deceleration, it fits the moon's recession, it fits 3 independent lines of evidence, radioactive decay rates that date the rocks, biological growth that records daily cycles, astronomical mechanics that predict how tides slow rotation, 3 separate physical processes, all converging on the same answer. The moon was closer. Earth spun faster. The system has been evolving for billions of years. Tidal rhythmites provide even stronger evidence, and these are sedimentary rock layers deposited in ancient estuaries and tidal deltas. Each layer represents a single tide. High tides deposit more sediment than low tides. Spring tides leave different signatures than neap tides. Monthly and yearly cycles appear in the rock. Geologists can count the layers and reconstruct day length, month length, and tidal range. In the 1990s, very old rhythmites were discovered in Australia, France, the Netherlands, Utah, Alabama, and Indiana. The Australian rhythmites from Ilatina Formation date to 620 million years ago. When sliced and analyzed in the lab, they show a day length of 21.9 hours. That corresponds to a moon distance roughly 12,000 miles closer than today. The recession rate between then and now averages 2.17 centimeters per year, about half the present rate. This doesn't mean the recession rate was constant, it means the average over 620 million years is slower than today's rate. The current rate may be unusually high because of near resonance between natural ocean frequencies and tidal forcing. Continental positions matter. When continents align to create large enclosed basins, tidal amplification increases, energy dissipation increases, the moon recedes faster. When continents disperse, tidal dissipation decreases, the moon recedes slower. Over geologic time, the rate fluctuates. Between 2 billion and 1 billion years ago, something strange happened. Day length stalled at about 19 hours for roughly a billion years. This finding comes from cyclostratigraphic analysis of Milankovitch orbital cycles in Precambrian sediments. The study, published in Nature Geoscience in June 2023 by Mitchell and Kirscher, compiled 22 Precambrian day-length constraints. 12 of those constraints came from the past 7 years. Statistical change point analysis shows a clear plateau. From 2 billion years ago to 1 billion years ago, day length didn't change much. This is called tidal resonance. The hypothesis suggests that atmospheric thermal tides driven by solar heating balance the decelerative torque of lunar oceanic tides. The two effects canceled out. Earth's rotation rate stabilized, the moon's recession slowed or stopped temporarily. This billion-year period coincides with what geologists call the boring billion, a time of relatively limited biological evolution and tectonic quiescence. It's possible that stable day length and stable climate contributed to evolutionary stasis, or it's possible that other factors were at play. Either way, the resonance effect is real. It's been predicted by models, now it's confirmed by data. The Earth-Moon system doesn't evolve smoothly. It goes through periods of rapid change and periods of stability. We're currently in a period of relatively fast recession. Now go back to the beginning, 4.5 billion years ago. The solar system is a chaotic mess. Dust and gas swirl around the young sun. Planetesimals collide and merge. Protoplanets grow. One of these protoplanets is called Theia, named after the Greek Titan who gave birth to the moon goddess Selene. Theia forms near Earth's orbit, possibly at the L4 or L5 Lagrange point, 60 degrees ahead or behind Earth. Theia grows to roughly the size of Mars, 10% of Earth's current mass. When it reaches that size, it becomes too heavy for its orbital position to remain stable. Gravitational perturbations from Venus nudge it. Theia's angular distance from Earth varies. Over millions of years, the variation grows. Eventually, Theia collides with proto-Earth. The impact happens about 4.5 billion years ago, around 20 to 100 million years after the solar system began to form. The collision is oblique, not head-on. Impact angle around 45 degrees. Impact velocity exceeds 9 kilometers per second. The energy released is staggering. Both bodies partially melt. Theia's iron core merges with Earth's core. Most of Theia's mantle and a chunk of Earth's mantle get ejected into space. Some material escapes into the solar system. Some material rains back down onto Earth, but a significant portion stays in orbit. This debris forms a disk around Earth. The disk is hot. Temperatures exceed 2,000 degrees Celsius. Rock vaporizes. Elements that evaporate easily, like zinc and sodium, boil off into space. The moon forms from the remaining material in this disk, Computer simulations suggest 20% of Theia's original mass ends up in the debris disk. About half of that material coalesces into the moon. The moon forms quickly. Estimates range from a few hundred years to perhaps a few thousand years. The newly formed moon orbits close, very close, about 2.9 Earth radii, roughly 16,500 kilometers from Earth's center. For comparison, the moon today orbits at 60.3 Earth radii, about 384,400 kilometers. The early moon appeared 14 times larger in Earth's sky than it does now. If anything had been there to see it, Earth after the impact spins fast, very fast. One rotation every 5 hours, maybe as fast as 2 hours depending on the impact, energy, and angular momentum transfer. The canonical giant impact model predicts a 5-hour day. More recent high angular momentum models suggest Earth might have been spinning once every 2 hours. Either way, Earth was a spinning top compared to today. The moon's gravity immediately starts raising tides in Earth's molten surface. The tidal bulge leads the moon because Earth rotates so much faster than the moon orbits. The tidal torque begins. Energy transfers from Earth's rotation to the moon's orbit. The moon starts receding. Earth starts slowing down. Over the next 4.5 billion years, this process continues, never stopping, never reversing, always the same direction. Earth loses spin. Moon gains orbital energy. The early recession rate was much faster than today. When the moon was at 3 Earth radii, tidal forces were exponentially stronger. The inverse square law governs gravitational force. If you halve the distance, you quadruple the force. If you cut the distance by a factor of 20, you multiply the force by 400. The tidal torque scales even more steeply. It depends on distance to the negative 5.5 power. When the moon was 20 times closer, tidal forces were over 3 million times stronger. Earth's day lengthened rapidly. The moon receded rapidly. Then, as the moon moved farther out, the rate slowed. The relationship isn't linear. It's a curve. Most of the moon's recession happened early. Most of Earth's spin down happened early. By 1 billion years ago, the moon had moved to perhaps 50 Earth radii. The day had lengthened to maybe 19 hours. Since then, the changes have been slower. The moon has moved another 10 Earth radii. The day has lengthened another 5 hours. The process is decelerating, but it's not stopping. Right now, Earth's oceans are the dominant factor. Without liquid water, tidal dissipation would drop dramatically. The solid Earth experiences tides too. Earth's crust flexes up and down by about 30 centimeters twice daily. The solid Earth tide also dissipates energy, but it accounts for only 4% of the total when measured by heat dissipation. 96% comes from the oceans. The oceans exist because Earth sits in the habitable zone, the right distance from the sun for liquid water. If Earth were closer to the sun, water would boil away. If Earth were farther, water would freeze. In about 1 billion years, the sun will increase its luminosity. It's part of stellar evolution. As the sun ages, it burns hydrogen more efficiently. Luminosity rises. Eventually, in roughly 1 to 1.5 billion years, the sun will get bright enough to boil Earth's oceans. When the oceans evaporate, tidal dissipation will plummet. The moon's recession will slow dramatically or stop. Earth's rotation will still slow due to solar tides, but the effect is much weaker. The sun accounts for only about 40% of the tidal effect that the moon does. Without oceans, the dominant mechanism driving the moon away disappears. This happens long before the sun becomes a red giant. The red giant phase occurs in about 5 billion years. At that point, the sun will expand to perhaps 100 times its current radius. It will likely engulf Mercury and Venus. It might engulf Earth. It will definitely engulf the moon. But the tidal story ends 1 billion years before that when the oceans boil. If oceans remained and nothing else intervened, Earth and moon would eventually reach mutual tidal lock. The same side of Earth would always face the moon. The same side of the moon already faces Earth. The moon is tidally locked to Earth. It rotates once every 27.3 days, the same as its orbital period. This happened early in the moon's history. Tidal forces on the moon were stronger than tidal forces from the moon on Earth because the moon is smaller. Its rotation slowed until it matched its orbit. Earth is much larger. It takes longer to slow down. But eventually, if the system had billions of years more, Earth's day would lengthen to match the moon's orbital period. At that point, both would be locked. Earth's rotation would equal the moon's orbit. The moon would hover above one spot on Earth. People on one hemisphere would always see the moon. People on the other hemisphere would never see it. At that point, the tidal bulge would align with the moon. No more leading, no more torque, no more recession. The system would be stable. Estimates suggest this would take about 50 billion years from now. Far longer than the sun's remaining lifetime. So it won't happen. The sun will intervene first. But let's talk about what the moon has done for Earth. Axial stability. Earth's axis tilts at 23.5 degrees relative to its orbital plane. This tilt causes seasons. In summer, the northern hemisphere tilts toward the sun. In winter, it tilts away. The tilt remains relatively stable over millions of years. The moon is largely responsible for this stability. Without the moon, Earth's axial tilt would vary chaotically. Mars provides a cautionary tale. Mars has two tiny moons, Phobos and Deimos. Both are captured asteroids. They exert almost no stabilizing force. Mars's axial tilt varies between 0 and 60 degrees over timescales of tens of millions of years. This causes wild climate swings. When the tilt is low, the poles are cold. Ice accumulates. When the tilt is high, the poles receive more sunlight. Ice melts and redistributes. Dust storms intensify. The climate becomes unpredictable. Earth avoids this fate because the moon's mass is large enough to gravitationally anchor Earth's spin axis. The precession of Earth's axis, the slow wobble that takes 26,000 years, is influenced by the moon. Without the moon, that precession would be erratic. Climate would be unstable. Complex life might never have evolved, or it might have evolved differently. We can't know for sure. But the moon's presence almost certainly contributed to Earth's habitability. The moon also affects tides in ways that shaped biological evolution. Tides create intertidal zones, regions that are underwater at high tide and exposed at low tide. These zones are extreme environments. Organisms living there must tolerate immersion and desiccation. They must withstand wave action and temperature fluctuations. But intertidal zones are also productive. Nutrients concentrate there. Sunlight is abundant. Many marine organisms evolved in intertidal zones before moving to fully terrestrial or fully aquatic environments. Some scientists speculate that the transition from water to land was facilitated by tidal rhythms. Organisms that could survive brief periods of exposure had a selective advantage. Over millions of years, those organisms evolved adaptations for terrestrial life. Without strong tides, this transition might have been slower or different. The moon's gravity literally pulled life onto land. That's not hyperbole. That's one hypothesis for how vertebrates colonized the continents. Tides created the selective pressure. Evolution did the rest. The moon has also stabilized Earth's climate on shorter timescales. The moon drives ocean mixing through tidal currents. This mixing redistributes heat and nutrients. It affects ocean circulation patterns. The Gulf Stream, for example, is influenced by tidal dynamics in the North Atlantic. Ocean circulation affects global climate. Changes in ocean circulation have triggered ice ages and warm periods throughout Earth's history. The moon's role in all of this is complex and not fully understood, but it's not negligible. The moon isn't just a passive satellite. It's an active participant in Earth's climate system. And it's been that participant for 4.5 billion years. Every tide that crashes on a beach is evidence of the moon's influence. Every coastal ecosystem that depends on tidal cycles owes its existence to the moon. Every organism that evolved in an intertidal zone has the moon to thank for the environment that shaped its ancestors. Now look at what we've learned from lunar laser ranging. More than 50 years of data, over 400,000 measurements, millimeter precision over hundreds of thousands of kilometers. The data has revealed more than just the moon's recession. It has measured the moon's internal structure. Lunar laser ranging detects the moon's librations. These are small oscillations in the moon's rotation. The moon wobbles slightly as it orbits. This wobble is caused by tidal forces and the moon's non-spherical shape. By tracking the position of the retroreflectors with millimeter accuracy, scientists can measure these librations. The libration data reveals that the moon has a fluid core. Not solid like initially thought, the core is about 20% of the moon's radius, roughly 350 kilometers in diameter. It's mostly molten iron with some nickel. The core's existence was confirmed by analyzing how the moon responds to tidal forces. A solid moon would respond differently than a moon with a liquid core. The data clearly shows the signature of internal dissipation at the core mantle boundary. This tells us about the moon's thermal evolution and its formation history. The moon was once much hotter. It had a magma ocean hundreds of kilometers deep. As it cooled, minerals crystallized out. Plagioclase floated to the surface and formed the lunar crust. Denser minerals sank. The core remained molten longest. Now, 4.5 billion years later, that core is still partially liquid. Still dissipating heat, still responding to Earth's gravity. Lunar laser ranging has also tested fundamental physics. Einstein's theory of general relativity predicts that the moon and Earth should fall toward the sun at the same rate regardless of their composition. This is called the equivalence principle. If Earth's gravitational self-energy doesn't obey the equivalence principle, the moon's orbit would show a detectable anomaly. Lunar laser ranging has measured this effect to incredible precision. The equivalence principle holds to better than 1 part in 10 trillion. This is one of the most stringent tests of general relativity ever performed. It confirms that Einstein was right. Gravity affects all forms of mass and energy equally. The moon's orbit is exactly where general relativity predicts it should be. No deviations, no surprises, just beautiful agreement between theory and observation. Lunar laser ranging has also measured Earth's precession with unprecedented accuracy. Precession is the slow wobble of Earth's spin axis. It takes 26,000 years for the axis to complete one wobble cycle. This wobble is caused by the Sun and Moon's gravitational pull on Earth's equatorial bulge. By tracking the Moon's position over decades, scientists can measure precession to fractions of an arcsecond per year. This data feeds into models of Earth's rotation and orientation. It affects satellite navigation. It affects astronomy. It affects anything that requires precise knowledge of Earth's orientation in space. The retroreflectors are still working. 5 arrays after more than 50 years. They were built to last. Each retroreflector is a corner cube. 3 mirrors arranged at right angles. Light entering the cube bounces off all 3 mirrors and exits parallel to the incoming direction. This property is called retroreflection. No matter what angle the light hits, it reflects straight back. The cubes are made of fused silica, optical quality, mounted in aluminum frames. Designed to survive temperature swings from minus 173 degrees Celsius in lunar night to plus 127 degrees Celsius in lunar day. Designed to survive micrometeorite impacts, designed to survive solar radiation and cosmic rays. They're still there. Still working. Apollo 15's array, 3 times larger than Apollo 11 and 14's arrays, handles 3/4 of all laser ranging measurements. Its larger size makes it easier to hit. Its retroreflectors are bigger, more photons return. The Apache Point Observatory fires a laser 20 times per second. Each pulse lasts 100 picoseconds. Pulse energy 115 millijoules. The beam spreads as it travels. By the time it reaches the moon, the beam is about 7 kilometers wide. Most of the light misses the retroreflector. Of the photons that hit the array, most scatter. Only a tiny fraction reflect straight back. By the time the light returns to Earth, the beam is spread to 20 kilometers wide. Most of the returning photons miss the telescope. On a good night, Apache Point detects 1 returning photon per pulse, 1 photon out of 10 to the 17th photons fired. The round-trip time is measured to picosecond accuracy. 7 picoseconds corresponds to about 1 millimeter of distance. That's the precision, 1 millimeter. Across 384,400 kilometers. The measurement requires accounting for many effects. Atmospheric refraction. The speed of light changes as it passes through air. The correction is calculated using atmospheric models. Relativistic effects. General relativity predicts that clocks run at different rates depending on gravitational potential. Clocks on Earth run slower than clocks in space. The correction is about 100 microseconds per day. Earth's rotation. The observing station moves as Earth spins. The correction accounts for the station's velocity. Lunar librations. The moon wobbles. The retroreflector's position changes slightly over the lunar month. The correction uses models of the moon's rotation. Ocean loading. The weight of ocean tides deforms Earth's crust. The observing station moves up and down by a few centimeters. The correction uses tidal models. All these effects are known. All are measured or calculated. When they're all accounted for, the residual is about 1 millimeter. That residual is the measurement uncertainty. It sets the limit on how precisely we can determine the moon's distance. And that measurement, repeated tens of thousands of times over 54 years, gives the recession rate, 3.8 centimeters per year, plus or minus 0.08 centimeters per year. The uncertainty is tiny. The measurement is rock solid. The moon is drifting away. Here's the final piece. The moon's recession isn't just interesting. It's one of the best proofs that the solar system is ancient. If the moon receded at 3.8 centimeters per year for the entire 4.5 billion years since its formation, it would have traveled 171 million kilometers. That's more than the current Earth-Moon distance. Obviously, the recession rate wasn't constant. It was much faster early on. Models that account for changing tidal dissipation over geologic time, changing ocean basin configurations, changing continental positions, all predict that the moon could have receded from 3 Earth radii to 60 Earth radii in 4.5 billion years. The models match the observations. The coral data matches. The rhythmite data matches. The laser ranging data matches. Everything fits. The only way to make it not fit is to assume the recession rate was always slow. But physics doesn't allow that. When the moon was closer, tidal forces were stronger. The recession rate had to be faster. The mathematics is unavoidable. The conclusion is inescapable. The Earth-Moon system is billions of years old. The moon has been drifting away for billions of years. It's still drifting away. It will continue drifting away until the sun boils the oceans or expands into a red giant. The story is written in laser data, fossil corals, sedimentary rocks, and orbital mechanics. The story is consistent across multiple independent lines of evidence. The story is strange, but it's true. And one more thing. The moon's drift is accelerating, not in terms of velocity, in terms of scientific understanding. We know more about the Earth-Moon system now than ever before. New studies published in 2025 using satellite altimetry show that tidal dissipation patterns are changing. Ocean stratification is increasing due to climate change. Warmer surface waters create stronger density gradients. This affects how tidal energy propagates through the water column. In some regions, tidal amplitudes are increasing. In others, they're decreasing. These changes feed back into the moon's precession rate. Not by much, fractions of a millimeter per year, but measurable, real, ongoing. The system is dynamic. It's responding to modern changes in Earth's oceans. The moon is drifting away from an Earth that is itself changing. The tides that push the moon outward are changing. The continental configurations that determine where tides dissipate are changing. Plate tectonics continues to reshape coastlines. Sea level is rising. Ice sheets are melting. All of this affects tidal dynamics. All of it affects the moon's drift. We're living in a moment where human activity is altering one of the most ancient processes in the solar system. The scale is small. The principle is profound. We're watching, in real time, as the Earth-Moon system evolves. 620 million years ago, tidal rhythmites in Australia recorded a day of 21.9 hours. 380 million years ago, fossil corals in New York recorded a year of 400 days. Between 2 billion and 1 billion years ago, day length stalled at 19 hours for a billion years because of tidal resonance. 4.5 billion years ago, Earth and Theia collided, and the moon formed in the debris. July 21st, 1969, astronauts placed retroreflectors on the moon. August 1st, 1969, scientists detected the first laser return. November 17th, 2025, Seoul, the moon continues to drift at 3.8 centimeters per year. The mechanism is tidal friction in shallow seas, 3.64 terawatts of power dissipating in the European Shelf, Patagonian Shelf, and Bering Sea. The result is Earth's rotation slowing by 0.0016 seconds per century. The result is the moon's orbit expanding by 3.8 centimeters per year. The result is a cosmic dance that has been playing for billions of years and will continue until the sun ends it. That's the reason the moon is drifting away. Not a mystery, not magic, physics, measurable, documented, undeniable physics. In 2015, a mass grave from the Viking Age was found near Dublin with silver weights matching Irish slave prices from contemporary deeds. In 2023, Armdeos, soil cores from Icelandic longhouse sites showed heat retention consistent with seal fat combustion and wall insulation thickness. In 2025, laser measurements from Apache Point continue to record the moon at 3.8 centimeters per year. Every number, every date, every source, they all point the same direction. The moon was closer, Earth spun faster. The system evolved, the evidence is carved in rock, written in coral, reflected in laser light. The moon isn't going anywhere fast, but it's going. And the reason it's going is stranger than most people imagine. Not because it's complicated, because it's so simple. Because it's been happening every single day for 4.5 billion years. Because you can measure it with a laser and a mirror. Because fossil corals prove it. Because sedimentary rocks record it. Because physics demands it. The moon is leaving, slowly, inevitably, and the ocean tides are pushing it away,